Welcome to Lecture 14 of Physics 506. This is entitled Nondegenerate Rayleigh-Schroedinger Perturbation Theory. This is the easy case for perturbation theory where none of the unperturbed energy levels have the same energies. You will see why there is a simplification, and we're going to be dealing with the more complicated case of degenerate perturbation theory in subsequent lectures. So we start off with the exact Schrodinger equation for our full Hamiltonian. H acting on an eigenstate n will give me an energy eigenvalue En times that state n. That's the classic eigenvalue-eigenvector relationship where the operator acting on the vector produces a number times the vector, indicating that the direction of the vector has not changed, but a number that multiplies the vector can come into play when the operator acts on the eigenvector. We're going to suppose that our Hamiltonian has two pieces to it, an unperturbed Hamiltonian we call H0 and a perturbation that we call V. In general, for perturbation theory to be valid, the V has to be small in some sense. I've described this in quotation marks. The H0 has to be something that we can solve exactly. And by solve exactly, I mean we know both the eigenfunctions and the eigenvalues exactly. So the unperturbed Schrodinger equation, H0 acting on the states n0 are equal to En0 times the state n0. Again, eigenvalue, eigenvector relationship, but now just for a piece of the total Hamiltonian. The non-degeneracy assumption is that E0n does not equal E0m unless m is equal to n. So every energy level appears only once in the spectrum, the set of all eigenvalues of the Hamiltonian H0. And this is called the non-degenerate case. Our goal is to try to find En and the states n, those are the eigenvalues and eigenvectors of the exact Hamiltonian or the full Hamiltonian, as a power series in the perturbation operator V hat. All right, so the way in which we do this is we write out explicitly the upper equation, Hn equals En times n, as H0 plus V acting on n is equal to E0n plus delta En times the state n, where En is given by En0 plus delta En. Now what we're going to do is we're going to rearrange this. We're going to bring the En0, or actually I'm going to bring the H0 over to the right-hand side, and I'm going to bring the delta En over to the left-hand side, and I'm going to just switch the orders. So we'll have En0 minus H0 multiplying the state n is equal to V hat minus delta En times the state n. What we would like to do is invert this, but unfortunately we can't just divide or take the inverse operator of En0 minus H0, because when that acts on the state n comma 0, En0 minus H0 acting on the state n comma 0 gives me 0, and I can't invert 0. So we have to find a way of handling and getting rid of that issue so that we can actually invert the equation in such a way that we can solve it. Now, the way that we do this is by working with what are going to be called projection operators. And to get you in the mood for thinking about projection operators, we're going to start by looking at the complete set of states, which involves Ket-Bra products of the unperturbed eigenfunctions. We sum that over all m, and from the completeness of the eigenfunctions of H0, we know that that summation is equal to the identity operator. So we're going to just let that En0 minus H0, when that multiplies this state, as I had mentioned before, you have a problem. We're going to have a problem when m is equal to n in the summation. So because the H0 acting on the eigenstate gives me E0m, when it acts on the eigenstate m comma 0. Remember, when a function is acting in the eigenbasis, I can replace the operator by the eigenvalue. So I can bring that En0 minus H0 inside the summation, and then I can evaluate it and replace the H0 by a E0m. And of course, you immediately see when we do that, that we run into a problem that this is singular when m is equal to n. If that summation did not include the term where m is equal to n, everything would be fine because we have a non-degenerate case, so there's only one place where the energies can be equal. But because we can't do that, that's why we have a problem. And we get rid of that by using projection operators. So let me define what the projection operators are. There's a projection operator onto the degenerate subspace and perpendicular to the degenerate subspace. So we define Pn, that's the projection onto the degenerate, onto the eigenvalue subspace. So the Pn projects onto the eigenvalue subspace. So it's the Ket-Bra product n0, 0, n. And then Qn is just 1 minus Pn. So remember, if I'm projecting onto some space, 1 minus the projection operator should project perpendicular to the space. So here you see then that the Qn is the summation for the completeness sum, except it explicitly excludes the case m equals n. Now, you may or may not have seen projection operators before, so I want to go over some of the properties of them. In particular, Pn plus Qn is equal to 1. That just follows from completeness. Pn squared is equal to Pn. That's easy to verify for Pn. I just multiply the operator by itself. In the center, I get a Bra-Ket sandwich. The Bra-Ket sandwich is the overlap of two eigenstates, but those eigenstates are normalized eigenstates, so that overlap is equal to 1. And you can see after I replace it by the 1, I get back the original projection operator. So Pn squared is equal to Pn. And then from the definition that Qn is 1 minus Pn, I can verify that Qn squared is equal to Qn because I just look at 1 minus Pn squared. I get 1 minus Pn plus Pn squared. Because Pn squared is equal to Pn, I'm going to get a minus Pn plus Pn, which will cancel and give me 0. I'm left just with a 1 minus Pn, but that's equal to Qn. So we also verify that Qn squared is equal to Qn. Another important point is that Pn times Qn is equal to 0. So I can't project onto the eigenspace and perpendicular to the eigenspace at the same time. You can easily see this from the definition because the overlap of the state 0n with the state m, 0 is equal to 0, because the states m0 include every state except the state 0n, and the eigenstates form an orthonormal basis of the Hilbert space. Similarly, you can verify that Qn-Pn is equal to 0. Now, because Pn-Qn is equal to Qn-Pn, that means these projection operators commute. Now, how do the projection operators act on operators? We just showed you how they interact with themselves, but how do they interact with operators? So a general operator I can write if I have an eigenbasis and the set of m sub 0 is an eigenbasis. I can write the operator as, again, the same or a similar Ket-Bra product, but that Ket-Bra product has a different index for the Ket and for the Bra. And then I bring in a set of numbers, OM comma M prime. If you like, OMM prime is the matrix associated with the operator. And that set of operators in that particular basis actually can be used to define the operator O hat. Or I can simply take products with the basis vectors forming a matrix element, M bra, M0 bra, M prime 0 Ket. And you can see the matrix element, that MM prime matrix element of O hat would equal OMM prime, which is those set of numbers. Now, if I look at Pn acting on O hat, I'm going to project with that N0, 0n Ket-Bra product, and the bra will hit, the N0 bra will hit the M0 Ket. That will give me a delta NM, and so it will immediately become ONM prime. If I hit with a Pn from the right, I will find that it is equal to ONN, N0, 0n. We can furthermore look at Qn acting on 0 hat. That's going to give me the set, but now my summation will be restricted for m's not equal to n. If I hit it with a Qn on the opposite sign, I'm going to be restricted to the set where m prime is not equal to n. And now if I have an operator in between, we can have these mixed terms. So I can have a QNOPN, which would just restrict my sum to be m not equal to n, and it will set the rightmost index to be n. And similarly, you can look at PNOQN. I did not write that down. What we say is that Pn projects parallel to the state n sub 0, and Qn projects perpendicular to the state n sub 0. And these are concepts you should be familiar with from linear algebra. Now, our claim is that the commutator of the operator Pn hat with H0 hat is equal to 0. We can easily check this. Pn times H0, you can see, just gives the number En0 times Pn. Similarly, H0 times Pn gives the same number times Pn. So obviously, those guys commute. Now, since Qn is equal to 1 minus Pn, we also will have that Qn commutes with the Hamiltonian as well. All right, so that's an important thing. These projection operators commute with the H0. Note, we did not say that they commute with the H, and in general, they actually will not commute with the H. All right, so let's go back to our original equation. En0 minus H0 acting on n, where n is the exact eigenstate, is equal to v hat minus delta En times the state n. We're going to now look at the state Qn times n. I'm going to, if you like, I'm going to just multiply by Qn on the left-hand side. And then after I've multiplied by Qn, and you see I can move that Qn all the way to the right to hit on the n state, then I can actually do the inversion. I have to multiply it on both sides. Then I can actually divide by En0 minus H0 because the Qn protects that result. It does not allow the En0 minus H0 to ever be 0 in the denominator. So let's carefully go through that and check that that works. Let's look. Qn times n is equal to the sum m does not equal n of m sub 0, 0 sub m multiplied by n. If I then divide that by E0 minus H0 times V hat minus delta En times n, I'm going to get the set of the sum m does not equal n of the ket m sub 0, and then the matrix element bra m sub 0 V hat minus delta En divided by En0 minus Em0 times the ket n. And you notice because m does not equal n and we have no degeneracy, that denominator is never equal to 0, so that is a valid result. Now, in addition, what we know is that if we do the summation m is not equal n of m sub 0 matrix element of En0 minus H0, that is equal to the sum m does not equal n of m sub 0, the matrix element of 0 sub m, v hat minus delta En, n. Now, the left-hand side, I can let that H0 act on the m sub 0 state to the left. It'll give me an En0 minus Em0. Now, because each coefficient of the m sub 0 must be equal on both sides of that summation, or if you like, we can just multiply by a bra that has a particular value of m. And because En0 minus Em0 is never equal to 0, what we find is that the summation m does not equal n of m sub 0, 0 sub m n is equal to the summation m does not equal n of m sub 0, 0 sub m v hat minus delta En times the state n divided by En0 minus Em0. What we're showing here is that because every term in the sum, term by term, must equal each other, I can then divide each term by term, by that coefficient, the En0 minus Em0, and then we get the result that we claimed we could get. So these are all showing different ways that you can verify that fundamental equation. Now, the issue is, of course, that the state n is equal to Pn plus Qn times the state n. Pn acting on n is the ket n sub 0, and then the inner product of n sub 0 with n. That tells us that n is equal to n sub 0 inner product of n sub 0 with n plus the term that we got with the Qn over En0 minus H0 v hat minus delta En times the full state n. What we're going to do is we're going to take that stuff that multiplies the full state n. You see that first term only depends on n sub 0, which is something that we know. We're going to take the stuff that depends on the full state n and bring them both to the left-hand side. So I'm going to get identity operator minus Qn over En0 minus H0 times V hat minus delta En. That whole thing multiplying the state n is equal to n sub 0, 0, n, n. All right. Now I think you're going to be able to imagine what we're going to do next. We're going to divide or multiply by the inverse operator of that big operator on the left-hand side. And then to get our perturbation theory, we're going to expand that in a geometric series. Okay, so what we find is that the state n is equal to 0n times the state n multiplied by 1 minus qn over En0 minus H0 V hat minus delta En, whole thing inverse, acting on the state n sub 0. By convention, we pick the overlap 0 sub n to equal 1. That means that our final state n is not going to be normalized. And so whenever we do a perturbation theory calculation, we always have to normalize at the end. So we do this because it simplifies the results in many places in the calculation. But you always have to remember that you have to normalize again at the end. All right, so what we're going to do is we're going to expand that term in a geometric series. So let's take a look at how that works. Our first term is the identity operator. That's going to just give me n sub 0. The next term is qn over En0 minus H0 V hat minus delta En times the state n sub 0. I can get rid of the delta En because that's a number. So the qn just moves through, but qn multiplying the state n sub 0 is always equal to 0. So that delta En can be dropped. Now the second term in the expansion is going to be the square of that operator. But again, that last term, because it's a number multiplying the state n sub 0, I can always drop that last number. And then the third term will be the cube of that big operator. And again, we can drop the delta En from the end. And we now, have this expression, and now we have to work with this expression to get the actual results that we're trying to get. So we have to think about systematically expanding the state n in a power series in V. That upper index of little m is indicating the powers of V. N superscript of 0 is n sub 0 because we start out coming from the eigenstate of the H sub 0 as the V hat is small. And then as the V hat grows, we will have more and more terms that we have to take into account. We do a similar expansion for the energies where En superscript of 0 is equal to En sup 0, the unperturbed energies. And the delta En is just that summation where I don't have the term where m is equal to 0. So it's a sum m equals 1 to infinity. Now, one of the key points is we need to know both En's and the state's n's up to the mth order in order to find the m plus first state. All right, so we start off, n superscript 0 is n sub 0. I already mentioned that. I'm going to move this up so we can see all of the results. N sub 1 will equal qn over En sub 0 minus H0 V hat acting on the state n sub 0. N sub 2 will equal qn over En0 minus H0 V hat minus En of 1 multiplied by qn over En0 minus H0 V hat times n. I have to put in that En of 1 because that's the first order change in the energy. N superscript 3 will be qn over En0 minus H0. I have an En2 from that second line that I did not include, that minus En2. I have to include that if I'm going to third order, times the qn over En0 minus H0 V hat, plus that triple term, qn over En0 minus H0 V minus En of 1, qn over En0 minus H0 V minus En of 1, times qn over En0 minus H0 times V, all acting on the state, the ket n sub 0, and so forth. It does get more and more complicated to work out what these formulas are for the higher and higher orders. It's straightforward, but complicated. You have to be careful. And again, as I like to say, that's French cooking. All right, how do we find the states En of m? Not the states, the energies at the mth order. Remember, we had our original equation, En of 0 minus H0 acting on the full state n is equal to V hat minus delta En times the state n. Let's multiply that by the bra n sub 0. Now, because H0 acting to the left is going to equal En sub 0, that left-hand side is going to equal 0. So what we find is delta En is equal to n sub 0 v hat n divided by n sub 0 n. But because n sub 0 n is equal to 1, again, this is the reason why we like to do that, we get that it's just equal to n sub 0 v hat n. And that now gives me a formula that I can use to do the calculation. Up here, we have the states n to a particular order. We have to multiply it by a v hat and take the expectation value with a n sub 0. Okay, so En of m is equal to n sub 0 v hat n of m minus 1. I only need the eigenstate out to order m minus 1 to get the energy eigenvalue out to order m. So let's work that out. En of 1, I take the 0 sub n, the v hat, and I multiply it by the n sub 0. That matrix element we call v sub nn. We're going to be labeling the subscripts of our matrix elements in terms of the indices that correspond to our unperturbed energy eigenstates. N sub 1 is equal to Qn over En0 minus H0 v hat n sub 0. Our prescription is to multiply by a v hat and then multiply by an n sub 0. So we're going to go ahead and do that. And I first am going to do the expansion and write the sum m does not equal n of Vmn over En0 minus Em0 times m sub 0. The way that we're getting that is by just plugging in the fact that Qn has that m ket, m sub 0 ket, m sub 0 bra product in it. And then I can easily see that I'm going to pull out a term that has a m sub 0 v hat n sub 0, and that's the matrix element we call Vmn. And now the En2 requires multiplying by a v and then multiplying by an n sub 0. That's going to bring in an extra factor of Vnm. So you can see that En of 2 is going to be the sum m does not equal n of Vnm Vmn over En of 0 minus Em of 0. Now because Vnm is equal to Vmn complex conjugate, that's equal to the absolute value of Vnm squared in the numerator. And the way we like to write that is the sum over m with a prime of Vnm modulus squared divided by En0 minus Em0, where the prime indicates you exclude the indices where that denominator would be equal to 0. All right, proceeding along, we can calculate n of 2. I can substitute in what En of 1 is because it's just equal to Vnn. And then I have to multiply that by a v hat and take the expectation value with a n sub 0 bra. It's a kind of a long calculation. You have to carefully work everything out, but it's pretty straightforward. And you can see there's sort of this pattern. It's like a zipper or a telescope. The first term is a Vnm prime, Vm prime m, Vmn. And the denominators are En0 minus Em prime 0 and En0 minus Em0. And then we have minus a Vnn times the sum over m with a prime, Vnm squared over En0 minus Em0 quantity squared. Okay, so that is different from the second order shift in the energy because it has a square in the denominator rather than just the denominator. And then this process can be continued to arbitrary order, but it really does get more complicated the higher order you go. On the homework, you're going to be looking at this through fourth order. Okay, so you'll be working out that correction. All right, this is a lot of formalism. You really don't cement this and learn it and understand it until you apply it to some problems, which of course you're going to get an opportunity to do on the homework. And that now takes us to the end of lecture 14 on non-degenerate Rayleigh-Schroedinger perturbation theory.